think are up. Did you get an email about the course evaluations? Please fill those up. Your feedback is welcome. Okay, that's one thing. The second thing is, so today we're going to finish up work on energy theorem, set 23. I think you solved some of set 23's problems yesterday, right? The last two. We'll try to solve the rest today. We'll finish up explaining the theory, and we'll solve more problems today. And then on Tuesday, we'll solve just more problems, maybe from the previous exams, and we'll do some more practice. If you have any questions, topic you'd like to review on Tuesday, send me an email or post on Ed. Then I'll make sure to prepare something about the topic you'd like to review. The midterm is going to be on Thursday during lecture time, 2 hours. It will focus on rigid bodies, but you cannot forget basically springs and frictions and all the concepts you learned before. But the focus is going to be on rigid bodies. There are going to be some short kind of questions and a couple longer problems. There are going to be a couple small derivation questions, so make sure you really understand all the derivations we're doing. They're going to be simple, really. Maybe I'll let you know. They will not involve tensors, but they'll involve other things that we've been doing a lot. Okay? Any questions? Yes? I still didn't finalize it yet, but I'm thinking 4 shortish, like 15 minutes each, and 2 30 minutes each, kind of longer problems. Yeah. And then the formula sheet you're going to have is similar to the one that's been given in the previous exams. Okay.
Can you give us the inertia tables?
Yes. So I'll see what you'll need in the problems, and I'll give you just those so that I don't have to do a lot of printing. Okay. Or I might just give you the value of, like, for a bar, about an axis perpendicular to its center of mass, passing by center of mass, it's this value. Okay. Any other questions? Okay. So the work energy theorem, well, we have 2 components of this. First, we need to define what the kinetic energy is, and then we'll write the theorem that is derivable from the balance laws. So the work energy theorem is not independent from the balance laws. It's the same procedure we did for particles, a system of particles. We're going to do for rigid bodies to derive this side. Now for this side of the board, we already derived the expression for the kinetic energy of a rigid body. So we obtained this at the end of lecture on Tuesday. How did we start with this derivation? Can anyone remember? How did we obtain the kinetic energy of a rigid body? Yes? Not quite. Yes, we did an integral. So what were we summing in that integral? Yes, dt, which was the kinetic energies of the differential masses. So if we have a rigid body, each differential mass dm has a kinetic energy dt that is equal to what? What's the kinetic energy of a particle of mass dm?
1 over 2 dm.
Exactly, dm v dot v. So this is the kinetic energy of the differential mass dm, and the kinetic energy of the whole body is just the sum of the kinetic energies of all the constituents. It's kind of an analogous to if you have a system of particles, the kinetic energy of a system of particles is the sum of the kinetic energy of the constituents. Okay? So this is how we obtain this expression for the kinetic energy. Now, in our particular situation, which is for this class where omega is along EZ, the expression for half ht dot omega simplifies. That becomes half izz omega squared. Why does that happen? So remember that hc is equal to ic omega. Okay, and that's, we can express that as a kind of, we can write this as a matrix times a vector to get a vector. Okay, now if omega is just along EZ, remember this is symmetric. If omega is just along EG, then HC becomes IXC omega EX plus IYZ omega EY plus IZZ omega EZ. Is that correct? Okay, and then what would happen if I were to dot this expression with omega to get HC dot omega? What will I get? Just that, right? So IZZ omega and I omega squared, and if I put a half, I'll get a half. So that's just a simplification up there. If omega is along EZ, which is the case in this class, then you can simplify the last term. Instead of calculating whole of HC, all you need is to know IZZ and multiply that by omega squared. Okay? Now there is another simplification that happens if the body is rotating about a fixed point O, then the kinetic energy, I can express it as half HO dot omega. So that expression will be equivalent to the bottom one, to this one. If the body is rotating about a fixed point O. Let us show this. So I'll start with the initial expression, half mvc dot vc plus half hc dot omega. Okay. And then if a body is rotating about a fixed point O, then what do I get? I can write that Vc minus Vo is equal to what? Vc minus Vo is equal to what? Vc, which is equal to what? Yes, omega. Yes, you're right, because Vo is 0. But that's also equal to omega cross Rc minus Ro. Perfecto. So I will replace Vc up there. Half m Vc dot omega cross Rc minus Ro plus half Hc dot omega. I want to take omega as a common factor, so I will remember my properties that when I have the scalar triple product, meaning a cross product and a dot product, I can switch these terms cyclically. So I can basically say that this is equal to, well, let us see. If I start with omega, then it's omega dot cyclically Rc minus Ro cross Vc. So I started cyclically. If that's 1, 2, 3, then I did 2, 3, 1. Okay? Any questions about this? Great. So then I can take omega as a common factor. Okay. So that's dot omega. I have a plus, well, the half is outside, Hc. And here I have an Rc minus Ro cross M Vc. Can anyone guess what this is? It is HO. Okay, so we proved that that's half HO dot omega. Yes?
Could you repeat how we came from
Yes, good question. So I just replaced VC here by omega plus IC minus R. Yes. Any other questions? Okay, so we just need to be careful of this. We can only use if the body is rotating about a fixed point. Okay, because in our proof we use the fact that the body is rotating about a fixed point. Yes.
So that term there, the variable, that's HO?
Yes, HO. Sorry. Okay, I think now we're ready to prove the work energy theorem. And the work energy theorem, we can prove it, it's derived from the balance laws. It's not an independent equation. Okay, so we will start with the expression for the kinetic energy and then we'll derive it. So T is half mvc dot vc plus half what was it? hc dot omega. And I'm going to take the derivative. How many terms am I going to get when I calculate the derivative? 4. I will need to use the product rule twice, right? So half m vc dot vc plus half m vc dot vc dot plus half hc dot omega plus half hc dot omega dot. Cool? The first two terms, can I do anything with them? I can combine them. And then what is this? I'll get the mv dot c dot vc. And what is this m dot v dot c term equal to from the balance laws? What is v dot c equal to? Right, exactly, from the balance of linear momentum, right? So v dot c is equal to ac. And we know that F is equal to m ac. That's our balance of linear momentum. So this term becomes F dot vc. And then plus we have these two other terms. I forgot the dot over here, right? What I want to show right now, any questions before we continue though? What I want to show right now is that half hc, well, this one I think, half hc dot omega dot, I want to show that's equal to half h dot c dot omega. And I'm going to do that using components. I'll take a shortcut and I'll just assume that omega is along EZ, but this is true even if the angular velocity is not just along EZ. Yes?
The first one is omega.
Yes. Okay. So let us see. I have that HC is equal to, so just to shorten the expressions, I'm going to just take that omega as along EZ. Then HC, we have it from there is IXZ. Okay, and then H dot C I have that the omegas and the bases, the quotational bases are functions of time, right? So I'll get I xc omega, well, I can say ex all of these times omega dot plus IXC What is omega cross EX? Omega is along EZ. EZ cross EX is EY, right? Yeah, and this is here. Okay. So I have that H dot C is IXC omega dot EX plus IYZ omega dot EY plus IZZ omega dot EX, sorry, EZ plus IXZ omega squared EY minus IYZ omega squared EX. Okay. This is a little bit tedious, but we'll do it. Okay, and I need to calculate H dot C dot omega dot. Oh, that's gonna be easy. That's gonna be just that. Sorry, H dot C dot omega. So that's gonna be IZZ omega dot omega. Right? And then if I want to calculate HC dot omega dot, what is that equal to? This is quicker to calculate. What is it going to be equal to? Exactly, the same thing. When this is HC, I can dot it with omega. Remember, omega dot is equal to alpha, which is omega dot, in this case, EZ. So that's going to be equal IZZ omega dot omega. So these two expressions are equal. This is also valid. Result also valid. Yes.
What's the significance of that last line? You say if omega is not equal to omega EX?
Easy. Sorry. So basically in this proof I said omega is along EZ and I proved this, but I can do the same thing even if omega is not along EZ, I'll get the same result, except it's going to be longer, a bit more tedious. Okay. Any other questions? So then with this result, what can I do to get my final answer over there? How do I proceed? Ideas? Yes.
Are you talking about up here for T dot?
Yes.
You're just gonna add them together.
I'm gonna add them together. Which form am I gonna use? So I'm gonna say that this is equal to half h dot c dot omega, and I'm gonna say that this is equal to hc dot c dot omega, adding the two terms. And what is h dot c equal to? mc from the balance law, the balance of angular momentum. Okay, from the balance of angular momentum, I get this. And this is my work energy theorem. Okay, and I can integrate this to get the form you're probably more familiar with. So integrating we get that t at t2 minus t at t1 is equal to the integral of f dot vc dt So what is this term here? The integral of f dot v dt. This has a name. Yes. What it is, the work energy theorem. So what's the name of this? It's just the work of the force F, right? This F dot Vc is the power of the force F. The integral of F dot Vc dt is the work. So that's the work of the force F from 1 to 2. Okay? And then here we also define the work of a moment. That's the work of a moment. Okay? So the work of a moment is just m dot omega, the integral of m dot omega dt. So be careful, we dot f with the velocity of which point? The center of mass, because here we're looking at which system? We're looking kind of at this system where we found an equivalent to the actual force distribution. This equivalent system has the force F acting at the center of mass and then a couple mc. So the work of the force F is the integral of F dot Vc dt. Vc is the point of application of the force F. Okay? So we can write the work energy theorem in a different form, which is this one, kind of having to do with this system. And then the work of, so we'll sum the work of the forces Fi, and you will see that the work of the force Fi is Fi dotted with the velocity Vi, which is the velocity of the point of application of the force. Let us prove this, and we'll do some examples that should be clear. So I want to derive the second form of the work energy theorem. Instead of using F and mc, I want to use all the forces Fi and the couple m sub e. Yes. Okay. Starting with T dot is equal to F dot Vc plus mc dot omega. First of all, how can I relate F, mc, and then Fi and me? So what is F equal to in terms of the other forces and moments? Yes, F is equal to the sum of Fi. What about mc? the moment of the couple plus the moment of the forces. How do I write the moments of the forces? What is it? But R is the position vector from where to where, so I'm trying to find the moments about the center of mass. So Ri minus Rc cross F, exactly. Okay, so I will replace this here. Any questions? This is important. We need to be able to do this. This is like statics-ish stuff, but it's important. Questions? Okay. T dot is the sum I equals 1 to n of Fi dot Vc plus Mc is Me dot omega plus the sum I equals 1 to n of Ri minus Rc cross F that is omega. Wow. Dotted with omega. I will expand the, well, oh, never mind. I already dotted with omega. This way. Okay, now it should look okay. Any ideas on what I should do next? This is the final form I want. Think about it. Chat with your neighbors. What should I do next? This is the form I want here. Yeah.
On this side of the equation, that's the moment of the couple.
Yeah. Me is the couple. Yeah.
Both that side and this one right here.
Well, actually, Me and MC are both couples. Pure moment. Okay, any ideas? Ideas? Yes. Can expand VC into what?
Like omega.
Well, we can say that VC minus VI is omega cross RC minus RI. Yeah, I think we can do that. That was not the way it was going to go, but we're going to try. I think it'll work. So that's the sum I equals 1 to n of Fi dot Vc, and instead of Vc I will put Vi plus omega cross Rc minus Ri. Okay, and plus Me dot omega plus sum I equals 1 to n of Ri minus Rc cross Fi dot omega. So this is sum I equals 1 to n of fi dot vi plus me dot omega plus sum I equals 1 to n of fi dotted with omega okay. So what do we need for these two expressions to be equal? We need that these two terms be what? Yeah, we want them to cancel. We want them to be 0. Do they cancel?
Yeah.
How?
You have to, if you did the permutation in reverse order, you'll get a negative on that last term. And then
So let's see, we can use the identities. So this omega, I can bring it inside. Like this. And if I have, okay, well, let us see. A cross B dot C, I can write as C cross A dot B. So I can write this as the sum omega cross Ri minus Rc dotted with Fi. And then these two terms will cancel out. Well, no. This was Rc minus Ri. And then I have Ri minus Rc and Rc minus Ri, and now they will cancel out. Because they're the same terms, except with the minus sign because this term is flipped. Right? And I think we're done. We've showed the two forms of the work energy theorem. Which one do you think you're going to use more often? I think the second one. Let us actually open set 23. Look at set 23. So let us look at problem 2. By the way, the same notions of energy conservation, they work for rigid bodies as they did for particles and systems of particles. So if you look at problem 2, the rectangular plate, pinned at its end O. If you draw the free body diagram of the plate, what are the forces acting on it? What are the forces acting on the plate? How many forces are acting on the plate? Problem 2 in set 23. Okay, so do you have set 23 open? Problem 2, okay. What are the forces acting on the plate? Yes? We have the reaction force at O and we have the weight. Right? The weight is acting at which point? Center of mass. Okay, chat with your neighbor. Is the energy of the plate conserved during its motion? Is the energy of the plate conserved during its motion? I'll take a vote in a minute. Okay, let's take a vote. Raise your hand if you think the energy of the plate is conserved. Raise your hand if you think it's not. Okay, we do not have a consensus. Chat again. Try to convince your neighbor. So what do you think? Conserved or not conserved?
I don't know. The reaction forces has to be workless. I don't know.
Is it workless?
I don't know.
Well, how do you calculate the work of the reaction force? Not cross, dot. Dot, the work of Fi dot Vi. And Vi is what?
Okay. So it was just like, it would forever go. Yeah, so it did.
What do you think? Conserved or not conserved?
Based on vibes, conserved because.
Vibes? What about the equations on the board?
Oh, at the beginning?
Yeah, I kind of think because there is an angular momentum situation happening, I think it's not conserved.
Well, let us look at this equation, the last equation we got, this one. T dot is this. Okay, I will integrate this with respect to time. I'll get T. What is the work of the force Fi from 1 to 2? What is the expression of that? It's the integral of this dt, right? And we have to be careful. Vi is the velocity of the point of application of the force Fi. And then the work okay. What is do we have any couples in this problem? No. So this term is 0. What about the work of the forces? Well, we have the work of the weight plus the work of the reaction force at O, right? The work of the weight, well, we know the weight is a conservative force. So the weight is a conservative force. We can write this work as a change in potential energies. It's going to be mg h2 minus h1. H is the height of which point? The center of mass, exactly, the point of application of the weight. Now, what about the work of the reaction force at O? What is that equal to? 0. Yes. Why?
Because it's not moving.
Right, because the work of the reaction force at O is the integral of RO dot the velocity of which point? O, the point of application of RO. And what's the velocity of point O? 0. So this is 0. So we get that the change in potential kinetic energies is equal to 0. Energy is conserved. Okay? Sounds good? The work of the reaction force at O? Great question. This is how we calculate the work of the force. The integral of F dot V dt. V is the velocity of the point of application of the force. So for RO, that would be the integral of RO dot VO dt. And what is VO? 0, because this block is pinned at O. So VO is 0, meaning that the work of the reaction force at O becomes 0, because this whole integral becomes 0. Okay? Okay, let's look at problem 3. Is the energy of the bar conserved during its motion? Take a minute, chat with your neighbors. Problem 3, is the energy of the bar conserved during its motion? The bar, I'm taking my system to be just the bar. Okay, raise your hand if you think the energy of the bar is conserved. Raise your hand if you think it's not. Well, not everyone raised their hands. Okay, again, let's take another vote. Raise your hand if you think the energy of the bar is conserved. Okay, great. Why is it conserved? Who can explain? I need someone on this side to explain to me why the energy of the bar is conserved. So how do we think about this? We'll help you out. Can you go ahead? Can you? Yeah?
So is it the same reason as before, but on the bar there's only conservative forces acting?
Well, actually, are there only conservative? What are the forces acting on the bar?
Tension.
The spring force, the weight, and the reaction force at O. Which of these forces are conservative?
So
The spring force and the weight. And what about the reaction force at O? It's not conservative, but what is its work? 0. Why? Because its point of application has 0 velocity. Okay, great. Any questions? Well, let's go back to problem 1. These two wheels are rolling without slipping down the incline. They're rolling without slipping. Is the energy of the wheels conserved? Yes or no? Think about it. So what do you think? Is the energy of the wheel conserved or not?
Yes, because it's just the weight acting on the wheel.
Is that the only force acting on the wheel, the weight? Normal force. What else?
There's no friction, right? Because it's rolling without slipping.
Could it be rolling without slipping without friction? If there's no friction, you can imagine it be like ice. You'll just slip down,
Oh.
like translate down.
Oh.
So there is friction. Okay, so now is the energy of the wheel conserved, yes or no?
No, because the friction is still.
Not. What is the work of the friction force?
I'm not sure.
How do you calculate it? Integral of f.
The velocity.
Integral of f dotted is the velocity of the point of application of the friction force. So where is the friction force being applied here? What's the velocity of this point if you're rolling without slipping?
Then it's changing. So then there is.
If the wheel is rolling without slipping, what is the velocity of the contact point between the wheel and the ram?
Zero.
So what is the work of the friction force? Okay, so is the energy of the wheel conserved, yes or no? Raise your hand for yes. Okay, who can explain? Yes. Well, actually, no, the middle. Can you explain? Cameron.
The fact that it's rolling without slipping means there is static friction.
Exactly.
There's some factor of energy that's going towards work. For the work, no.
So is the energy conserved or not?
If you include that, then maybe.
Well, let's go back to our method. We have the wheel. We have the force acting on it are the weight, right? And then the normal force and the friction force. Okay? This is conservative, right? What is the work of the normal force during the motion of the wheel? Yes, why is it 0? It's rolling without slipping. So what's the velocity of this point, the point of application of the normal anti-friction force? Right, so Vp is equal to 0. So the work of the normal force is 0. And what about the work of the friction force? It's also 0. Okay? The integral of ff dot Vp is 0. So, is the energy of the wheel conserved? Yes. So technically it'll go on. If we release it like this and it's rolling without slipping, it'll go on forever. Yes.
So, energy is conserved in this case.
Mm-hmm.
Also identically conserved when it's fully slipping.
No. So why is the energy not conserved when it's slipping? Because the velocity of this point is not 0 anymore. Okay? Let me ask you this. If I have the disc on the truck, you worked on the exercise, right? The cylinder on the truck bed. Okay, assume that the cylinder is rolling without slipping and the truck is moving. Is the friction force workless, yes or no? Raise your hand for yes. Raise your hand for no. Is the friction force workless? What is the work of the friction force? Raise your hand if you think the work of the friction force is 0. Raise your hand if you think it's not 0. Okay, chat about it, think about it, discuss. So what do you think? The work of the friction force, 0 or not?
I think it's not 0.
Why not?
The truck is moving, so there's some sort of velocity at the point of contact.
Mm.
So it's
Yeah. So what do we think? The work is 0 or not?
if it's rolling without slipping, then yeah.
Is it slipping?
No, it's rolling. It's rolling on the truck bed, but the truck is moving. Okay, figure it out. I'm going to call on you in a minute. Okay. Is the work of the friction force 0? Raise your hand for yes. It's 0. Raise your hand for no. It's not 0. Okay, it's 0. Can you explain why? Well, in the previous problem, the point of application of the force had 0 velocity. So when we were calculating its work, we integrated f dot Vp, and what is the velocity of P? It's 0, so the work is going to be 0. Is that the same in this problem? If I look at point P, what is the velocity of point P? Since the cylinder is rolling without slipping on the truck, then what's the velocity of point P? No. The same of that, yes, the same as the velocity of the truck. So then, is the work of the friction force 0? No, what is the work of the friction force? That's going to be the integral of the friction force dotted with Vp, and Vp is not 0, right? So this answer is going to be non-zero.
But if we take our coordinate system
To be on the
to
truck.
yeah, so
Did I say that Vp is viral? No, that's not the. That should be the absolute velocity, not the velocity observed in some moving system. Okay, remember our balance laws? They apply in a fixed coordinate frame. Okay? Okay, let's do some more games. The problem 4. Any questions about this? This is important. Yes?
So if you did take your frame of reference to just be those two objects,
The issue is you don't get to choose your frame of reference. It needs to be inertial. Velocity, that needs to be the absolute velocity of the point of application of the force. Okay?
but relative to the truck, it does no work because it keeps everything going.
But work by definition, you have to use an inertial frame because when we define the work energy theorem, we use the balance laws, balance of linear momentum, balance of angular momentum that only apply in an inertial frame.
Okay, so that includes like the outside world, so that
that's
V
what
is
I.
Yeah. So V and omega are defined relative to a reference configuration that's fixed.
But isn't the truck an inertial system by itself because it doesn't have
No. Good question. I'll get back to you on that later. Cause yeah.
Think about you want that rolling a cylinder rolling up a hill, right?
Mhm.
40? 240. For one person? Yeah. The solar system and power. What at velocity? That means nothing.
Yeah. Well, for us, we're taking an inertial frame to be a frame fixed to the Earth. Yeah, that's where Newtonian mechanics holds. But I mean, you could argue that Newtonian mechanics like doesn't hold anywhere because nowhere is fixed, and then you have to use a relativity basically. Then you're in another theory. Okay. Okay, problem 4. Is the energy of the bar conserved during its motion?
Wait, velocity here is 0, the reaction force, and it's just one force going down. I think it's conserved.
Okay. Raise your hand if you think the energy of the bar is conserved. Raise your hand if you think it's not. Okay, I think we have a consensus. It's conserved, right? Because the only two forces acting on the bar are the reaction force at O, that is workless, and the weight acting by center of mass, which is conserved. Okay, now problem 5 is a little bit more complicated because it consists of two rigid bodies. Okay, and to write the work energy theorem of a system of rigid bodies, we have to write the work energy theorem of each rigid body and add them. Again, the work energy theorem for a system, be careful, careful. The work energy theorem for a system of rigid bodies, you write the work energy theorem for each rigid body and then you add them. So can you go ahead, draw the free body diagram of each bar and then write the work energy theorem for each bar on its own, and then the work energy theorem for the system. So I know you solved this yesterday, but I want to make a point about it. So draw the free body diagram of each bar, write the work energy theorem of each bar and of the system. Again, free body diagram of each bar, work energy theorem of each bar, and the combined.
Velocity here is 0, so it's a fixed point. So these two reaction forces.
your free body diagram, you have to isolate the system. شو قد understand.
That's a moment, so it's like
So when you draw the free body diagram, you remove the support, basically. You isolate the system. So you need to remove that pin, though. No?
Well, but this is still here.
Yeah, you remove the pin, then the reaction force is going to show up.
it's not accelerating in the left, it's left or right. There's not being forced in the left or right.
Not why?
I think so.
The energy is not for sure. Right, can you label the forces and write the work energy theorem?
Force in the left, there's no constant force.
Either way, it's moving might be making it.
And the work energy theorem.
And then
Okay, let's draw the free body diagrams together. So what are the forces acting on bar AB?
So reaction force A.
Yes, is it the reaction force or is it a normal force? Normal force, because it's a roller at A. Okay. So NA, we have the couple. They call it M. What else?
Weight.
Weight.
And reaction force B.
Reaction force LB. It's not vertical, so RB. Okay. What about on bar OB?
So reaction force of M.
Minus RB. Action reaction, right? What else? Weight. What else? Reaction force L. Okay, let us look at these forces. NA. What is the work of NA? 0 or non-zero? 0. Why?
Because the product is 0.
It's perpendicular with the displacement. So this is workless. These two forces, the weights are conservative, right? RO,
0.
workless. Do we all agree that RO is workless? What about RB?
Has work.
Does work. What about minus RB?
Has work, but like it's opposite.
Does work, right? A couple, actually a constant couple, like a constant force, is conservative. So this is conservative. Okay? So if you want to find the work of a couple from 1 to 2, that's the integral of m dot omega dt. So that's equal from t1 to t2. If m is a constant, then I can take m outside. That's going to be dot t1 to 2 omega dt. And what's the integral of omega dt? Yeah, basically theta t2. Easy. So the work of the constant moment only depends on the end states, the end kind of rotation of the.
Like the couple for couple like the torque, right? It's adding energy to the system, right?
Yes. potential energy, because I can look at the work of the moment as a change in potential energy. Okay? Yes?
Did we not include the wheel at A?
The wheel at A, is it massless? If it's massless, then we do not include it.
But we do have the friction of it rolling,
Um,
or is that also work?
yeah, that's worthless because it's running without slipping. They don't mention the mass of the wheel at A side. I think it's massless. I assume to be massless.
So we will assume that will, like, no matter the speed moving, the wheel will move without slipping, right?
The wheel will move what?
Will move without slipping, right?
Yes.
No matter the speed you have.
Yes, yes. Okay. So then for each bar on its own, is the energy of the bar conserved? For each, so is the energy of bar AB conserved?
Yes.
Oh no.
No, because of B. And here, also no, because of B. However, if I consider the combined system of the two, is the energy going to be conserved? Yes. Because the work of this force here and the work of this force here, what are they? They're opposite. Because the work of this force is the integral of RB dot VB. The work of this force is the integral of minus RB dot the velocity of that point VB. So the two works are opposite, they're gonna cancel out. So if I write the work energy theorem for each bar on its own, for bar AB at T2 minus TAB at T1, that's equal to the work of the weight AB plus the work of the couple AB, or the couple just 1, 2, 1, 2 plus the work of RB 1, 2. And the work of the normal forces here. BO okay, these are conservative. Okay, if I sum these two equations, these two go away. So I get that the change in kinetic energy is the change in potential energy, or minus it, so the energy is going to be conserved. So for the combined system, the energy is conserved. But, caution, it's not always true that we can neglect the internal forces in the work energy theorem. For example, I could have this system, same here, okay, and I can have a damper between the two. Okay, can I neglect the damping forces and say that the energy of the system is conserved? No, even though the damping forces are internal, I have to calculate the work of the damping force on this and the work of the damping force on this. Here it's going to be 0 because it's applied at a point with 0 velocity. Here the work is going to be non-zero because this is moving in the same direction as the damper force, and the energy of the system is not going to be conserved. So we have to be very careful that when calculating the work energy theorem for a system, we have to take into account the work of the internal forces. For example, you solve the problem, this one. In one of these sets, you had like a pendulum that's being driven by a motor, and this happened on a cart. Remember that problem? Not my best sketch, let me fix it. Remember that problem? It was in one of these sets. That's an important problem. If you haven't solved it, please solve it. But in this problem, you had an internal motor here that's rotating this pendulum, and this causes the cart to go back and forth, to move, translate basically. So as the pendulum moves, the cart goes back and forth. Is the linear momentum of the cart conserved during its motion? Yes, because the sum of the external forces is 0. Is the angular momentum of the cart conserved during its motion? Yes, because if this is giving a moment, that's going to be a reaction moment. Is the energy of the cart conserved during its motion? No, because the motor is providing energy, right? So we have to take into account the work of the motor. Yes. The work of the motor that is providing a couple that is turning this pendulum. Okay?
So,
Yes.
What about the damper though? The damper isn't providing energy,
It is taking out energy.
but it's still, the damper is part of the system. The energy is being transferred from one location to the system.
No, this point is not moving. So the work, so if I draw the free body diagram of the system, it's going to be the same as this, except here I'll have the damper force and minus the damper force, right? The work of this is what? 0, because it's being applied at a point with 0 velocity. The work of this is what? Non-zero.
Yeah, I understand.
So it's going to bleed up, and it's actually opposite to the velocity of that point. So it's going to bleed out the energy of the system. So eventually our system is going to stop.
So, am I right by saying that damper is some sort of like spring, right?
It's not a spring. It's you can think of it as like friction. Basically, it's there's friction inside of it. Things rubbing or because of a fluid inside, a viscous fluid, it takes out the energy of the system. So it provides a force that's opposite to the velocity.
Because
The spring provides a force that's proportional to the deflection of the spring.
It has no friction, so like you don't lose energy basically.
Yes.
For the cart rolling, right?
Yeah.
There's like a motor, right?
There's what?
Motor. On the
Motor. Yes. There's a motor here in the cart that's turning the pendulum.
Is it providing like constant torque? And you have like rotating object with constant.
I don't remember in the problem if the torque was constant. I wasn't sure. Or if omega was constant. But
okay.
what's your? Yeah, I'm not sure.
But if it was both of those constant, the angular energy constant too, right?
The angular energy?
Like
The angular velocity? No, I don't think so. The motor. We'll actually need to solve this problem to figure it out. If the moment is linear with omega, or if there are other terms that come in.
Okay. Because I'm asking because I'm still a bit confused why Adam like considered conservative and why like.
So by definition, a conservative force or a conservative moment is derivable from a potential. So I can say that the work of this moment is just the potential at this minus the potential at time t2 minus potential at time t1.
How I imagine like right? We have like this system, right? And then, for example, have like a bar.
And by the way, this is only applicable in 1D, where omega is along EZ and the moment is along EZ and constant. Yes, continue.
Yeah, I rotate it like by hand, right? So I'm like adding like external torque, and that will be our M.
Well, you can think of gravity as adding a velocity to a ball that's falling, but we still say that the energy of the ball is conserved.
Okay, yeah, that makes sense.
Okay, great. Let us solve a few problems, as many as we can. Can we start with problem 1? Well, start with problem 3, then problem 1. Then we'll see if we have time for problem 2. I'll give you the quiz papers. Start with problem 3, and you can work in pairs, but I'll take one paper per person.
Same set, right?
Yeah, set 23. Okay, if you have questions, let me know. Let's try to finish up this set today, so that in the weekend you can solve like the rest of these
I have a
sets and the previous examples. Yes.
So for conservative force, we have four options, right? We have gravity, weight,
Spring force.
spring, and constant forces. Any constant force?
Yeah.
Okay. So that means that like the damper or friction or any of those, they have to be non-constant in order for the work to be non-zero or not. Yeah.
Yeah, so that they're not conservative.
Okay.
Which is true. The damper, we take it to be proportional to the velocity.
Okay. Got it. All right. Thank you.